I hope you have a nice weekend. So today we will finish this topic, topic 3 for random variable. I will put the assignment on after today's class. You'll be give you a little bit more generous. I will give the next Friday, not this Friday. Next Friday will be the deadline. So basically, you got 14 days, at least more than, yeah, more or less like more than 10 days, right? So let's very briefly what we're doing. Today we will do mainly for this topic we will do some Excels, and then we will talk about the after the break probably is after the talk we call the sample distribution. So very quickly we review random variable. I'm not going to review one by one, but just quickly go to the things we want to talk about. So basically, if you have already got understand what happened in the last class already, you know how to do the homework, because today we just covered T and F, which will not appear in the homework, but will be useful in the later stage. So just a very gentle reminder, what is random variable? It's a way you give a number to outcome of a random experiment. The reason is being that it can be very complicated, and we only care about probably the number they generate from the outcomes, okay? And it's easier to handle. And depend on what kind of number you can assign, and it divided into discrete and continuous. Discrete is usually there's a finite number of outcomes, and usually we call the natural numbers. When you do counting, then it's very natural. You have a discrete random variable. For continuous, is the case where you assign that common number, right? That's happened usually where you talk about financial number, accounting numbers, stock market, prices, quantities. Those are kind of thing that you use continuous, right? But the way you distinguish them is what artificial, in the sense that it's the math tools that you use them, right? And then you sometimes it's convenient to talk about discrete, sometimes it's more convenient to talk about continuous. Depends on the nature of our application. And regardless of the way you define discrete continuous, right? We can we have to have some way to describe them, right? For discrete, you have the P, big P, and you also have the big F, and big P and big F are closely related, as you know already, right? I'm not going to talk about those. And based on the F and P, we can define expectation, right? And also we can define variance, right? By expectation, you mean actually you repeat the experiment and you calculate the mean, and the variance are the same idea where you outcome you minus the mean and square, and that will be the average of that quantity will give you the variance. And then we know various formula to talk about mean and variance, okay? And there's some formula for the sum and formula for the those things. And in particular, we learn the main several distribution that will be useful, right? And basically, although we say 5, actually there are actually 3 or 4, right? Because BINOM is a special case of binomial, right? And Poisson is a special case of binomial as well, right? So binomial, probably you remember, is that repeating the same experiment again, and each time it just records success or failure, right? And that is a binomial. And Poisson is the way you try to count number of people or number of events that happen within a period of time, right? And the important thing is non-overlapping region is independent, right? Because it's following from binomial, right? It's each trial is independent. So for the time idea of the Poisson is the same, right? if there are 10 people coming in the first hour, it doesn't affect the probability you assign for the subsequent hour, right? So what happened before doesn't relate to what happened after, right? So same idea of exponential, which we'll talk about later. And hypergeometric is the idea where you're talking about sampling with replacement, right? So without replacement, which is essentially talk about audit and quality control, right? So I'm not going to talk about this because we reviewed that too many times already. So I'm going to quickly review the continuous random variable where there is the something we didn't review only once, right? So just to remind you that why to describe continuous random variable, we don't use P. We don't expect P. The reason is being that when you have continuous random variable, the random variable equal to a certain value is 0, right? So P of X will be horizontally flat at 0. So there's no point to talk about that. But there's a meaning of F is the probability less than or equal to a certain value that is a meaningful thing we can define as F. Right, so that's the reason why we don't talk about big P, because big P will be constant at 0. So that's why we don't have that. And although we don't have big P, but we have something similar to big P here, which is the small f. So that's why we have small f here, is because they play similar role. And but instead of talking about the probability at certain value, we talk about the probability that the random variable within some value, and that is based on the area under the curve of little f or small f, right? I'm not going to repeat those. I think we know in the very well how to do it. Okay, and the same idea you can apply to the expectation and the variance. And here we have integration because of the way that the math tools require. And as I said, I mean, we don't expect you to learn calculus, so this is just the formula that you know what's going on. If you know calculus, that would be obvious. If you don't know, it's okay. You just take my word as given. It's just standard idea. You just repeat the random experiment many times, and you kill the average. Is what we are seeing here. Okay, so this is nothing very deep here except the we have just said. Okay, so here we basically learn almost everything we will encounter in this semester. We focus on the first 3, and the last 3 indeed will be used for the rest of our course. But here we just introduce to you at the very beginning, so that when you see it, you don't feel too much an alien. So let's talk about the first one. Is uniform, but uniform is just a way to let you see the small f and big F it looks like, and also is a good way to model at the first round. Okay, so this is what the small f and big F looks like, because it's uniform between this. So the area under this F curve will give you probability, right? So I'm not going to repeat the small f and big F is able to see this. Okay, and so here is the mean and the variance, and that is not surprising because uniform between A and B, so the mean must be in the middle of the interval, right? And the variance will be square related to the square of the distance, and the denominator 12 is something coming from formula. You do integration, so I don't have a good intuition for that, but I hope it's being clear what we're doing here. And the next thing, exponential, that is a good cousin of Poisson. And then if you remember what is exponential, it essentially said if you have a period of, you have a period of time, you have a Poisson idea, right? A Poisson of mean lambda, and we are talking about when the first event happened, right? Poisson is asking within a period of time, how many events would happen, and Poisson is asking at what time that would be happen. So just to make sure you get it, just to remind you, the Poisson is like this, right? For a period of time, right? And you cut this into very small sub-interval, right? This interval, right? And where each small interval, right? Right, because this is time t, so each interval is just t over n, right? And we put, and we have n go to infinity, okay? Or n is very big, so that's why you cut the time horizon height interval into very small subinterval, and each subinterval has success of p, right? So Poisson is asking how many events will happen overall the period t, right? And each subperiod has probability p, and what we have in the limiting case is called np is equal to lambda, n go to infinity, right? And that means actually means go to infinity, so p is going to very small, right? Because when the times together is a constant lambda, right? So that is p is going to be very small. But they multiply together is still lambda. And lambda, remember the Poisson is a case, this is on average how many events happen within this period, right? So the exponential actually means suppose this thing happened here, okay? And one event happened here, right? And we say the this is a Poisson with x equal to 2, right? That 2 events happen, right? But for exponential, we will say this is, sorry, this is a color. So this would be the time that t, we just look at the first success, right? How long does it take for the first success? That is the exponential. So this is the exponential idea, okay? And actually, we don't ask what about second success. The idea same Poisson, or what we call is independent, or what we call the memoryless property. So this is also exponential, because once you have done, you count it again, it's still exponential. Okay, so it doesn't really matter the first success or second success, the same thing, because that is what exponential means. And as you can see, if I say t is an hour, say suppose, right? T is an hour, 1 hour, right? Suppose t is 1 hour, okay? And I expect 2 events is going to happen here, right? That means I have 1 event here, 1 event here, right? On average, right? So that means that how long does it take for the first success to come about, right? Is half an hour, right? Because 1 hour you have 2 events, so we expect the time it takes for the first thing to happen is 1.5, right? So that's why when lambda is 2, right? For exponential, will be the mean, right? Will be 1/2, right? So that is why the mean of exponential is 1 over lambda, right? The reason is being that if you happen, the event happen at the rate of lambda, the time you take for event to happen is 1 over lambda. Okay. So the reason why I talk about exponential, because this is different from normal, right? Because normal, I mean, if you recall, can be any value from negative infinity to positive infinity, right? So you allow negative numbers, right? But when we talk about time, I don't think you want to talk about negative time, right? I mean, at least as far as we know the physics world, and then we don't allow negative time. So when modeling the time things to happen, it's better not to use normal, right? I mean, better use the exponential, right? And you probably, as I mentioned, I mean, if you believe that your process or your model, that your time that you're trying to model satisfy the memulous property, then exponential is the only way you can do it, right? Of course, you think that what happened in the past have the impact on the future, then probably exponential is not a good thing. But nevertheless, if you don't have idea how it relate, then exponential would be a good approximation to what you're doing. Okay. I hope that's clear why we talk about exponential, right? Because of modern time, although normal has a lot of usage, but still you don't want the time to be negative, right? Because you present to your boss and then you get the mean can be negative, or the boss will ask why you use that, right? But if you have a time, your exponential is the pretty good reason to not to screw up. Okay, and one important thing is about the variance, and we don't have good intuition right now, but the mean is different from variance. Okay, and that is slightly different from Poisson, right? For the Poisson, the mean and variance are the same, but for exponential, it depends on the lambda. It can be smaller, can be bigger, but the variance can be will be different from mean in general, right? Sorry. So I would like to draw your attention on the normal distribution, also called the famous bell curve, and just to remind you the details of it, because we'll be using it for the rest of course. So I mean, it's okay to spend a little bit time on this. And for the bell curve, it is indeed a very common thing, and then we'll probably explain 2 weeks later, and then you would know why we have normal. And the reason is being what we call the central limit theorem, right? Just to remind you that it is because of the fact that IQ weights or height are determined by many factors. You can consider average of those factors, so that's why normal would fit, and that generalize the idea to sampling, right? Because you collect the sample, you calculate the sample mean is indeed the average of many individuals, and at the end of the day, then there will be a bell curve. So that's why for our course, the bell curve is very important. It's because it's what we care most of the time is the average of the observation of the samples. So that is the reason. But you will see more clearly why we have the bell curve for the rest of the course. And besides, it's very simple. Okay. And another reason why normal is good is because it's simplicity, right? Just remember, for normal, you just need to look at the mean and variance, right? Because of the skewness and kurtosis is always the fix, right? The skewness is always 0, kurtosis is always 3, right? And the only thing for the bell curve, you only need to care about the mean and variance, which is mu and sigma square in the small f and big F. And particularly the mean and variance are separated, right? Because you look at other distribution, mean and variance are closely related. But for the normal, the bell, mean and variance are separated. And mu control the location, and sigma control the tall or the fatness of the tail, right? How tall the peak or fatness of the tail. They're very similar. And not going to go into further details here, but we know that when you're normal, the transformation is still normal. So the bell curve, you multiply something plus something is still a bell curve. So which is a very important property. Of course, the main thing, of course, this leads to the idea what we call standardization, right? So we just subtract the mean over the SD will give you a Z, which is standard normal, which we know how to check our table, right? And then I think we talked about that last time. I'm not going to talk about this anymore because today we talk about Excel. We talk about how to do Excel on this, okay? Although we do it the table form, but we would try to tell you how to do Excel. And unfortunately, in the exam, you have to look at the table. But for the assignment, for your project, you can use Excel without any issue. Okay, but there's a limitation. Okay, and here probably you will know this by the end of your semester. Where is this rule of thumb or empirical rule or 3 sigma rule or 68, 95, 99 rule, which is a rule that probably, even though you ask anyone who haven't taken statistics for a very long time, or they have after many years, they probably will still remember this rule, particularly the second one, the 2 sigma rule. Is like the probability that Z is between -2 and 2 will be 95%. Okay, so basically it's just this graph, and within 1SD 68 and 3SD 99. Right, so that's why one of the application is, if you know the mean and you know the SD, then if you believe that is normal, then you will probably know how well you're doing, right? In the midterm, probably you're doing some of the class, right? When you know for the mean and you know the SD, then probably you know how well you are doing, right? Suppose that for the sake of discussion, right? Suppose you say in the midterm the mean is 70, right? The SD is like, I don't know, 5, right? So suppose your score is like 80, right? Then it probably means that you are pretty well, right? Because you already 2 SD above the mean, right? Because more or less you have been, I mean, better than 95%, right? Actually more than 95, but at least you're doing very well, right? Assuming things are following a bell curve, which usually okay. And if you are doing 60s, then actually you are not doing very well, although it's just 2 SD from it, right? But it basically said you are 2 SD, and maybe you're really close to the bottom, right? And then the question is asking, people, you ask, what about 65? Are you doing good? And again, the problem is like not very good as well, right? Because of around 70% is nearby the 1 SD, right? You're at the boundary as 1 SD, then probably at the end you get a B- and B if you continue on that path, right? So that actually gives you a very good idea how well you are doing relative to the mean, right? And as well as median, right? And of course, I mean, if the data is, if the underlying data is not following this normal, then you need not worry too much, right? Because probably you should ask your teacher probably what is the median, right? If the median is far away from the mean, probably the bell curve is not really a good approximation, right? So just keep, I mean, we assume normal, then this thing apply, right? If not, then it's not applying, right? So we probably should ask, what is the median, right? If you know the median, if median is close to the mean, then probably the bell curve is a good approximation to what we should do, okay? And anyway, so I'm not going to go into the further details. I guess that would be. So the final thing we talked about last class is this normal property is saying that if you have 2 bell curves, you add up, it's still a bell curve, you subtract still a bell curve. So I basically add them to the slides. You see if a bell of this and bell of that one, add them is still a bell. Okay. And do note that add them up, the bell will be more flat because the variance add up. Okay. And when you subtract the 2 bell, the same idea goes in, but the variance still, oh, sorry, this is a typo here. It should be plus. Okay. So the variance still a big one. Okay. So I hope that is clear, but I think we have drawn it in the class, so it shouldn't be an issue. I just put there in case you want a more perfect slide, so everything in old slide would be working. You don't need to download them. If you already have the class, you write down that. So for the remaining time, I want to talk about the quickly talk about the chi-square, T and also F, okay? So we are not using that at the moment, but you will be soon clear what they are those, okay? And very quickly, we just give you the definition because we'll just apply directly, okay? Because they're very close to normal. So what are those is actually not that difficult, okay? Chi-square, if you remember, it's just x squared. X squared in our sense is just z squared. It's standard normal square. So actually it's the first statement here, okay? That means that if I have a bell curve, okay? The bell curve is here, okay? And I just imagine that I take a value here, okay? I draw some value here. Once I draw it, I take a square, okay? And do the same for every entry, right? Something like this may comes out, right? It will be very much like the bell curve, right? But you will start from the negative, right? You would never go to negative because square. So this is a chi-square, okay? Degree of freedom 1, okay? And actually, I have the graph in the next set of slides. It's like the red one, okay? It's a bell curve, but you just basically flip to the other side and you square, okay? So we just like a one-sided bell curve, you can imagine. The one-sided bell curve, okay? Just because the bell, you square the thing, it's just like more likely to squeeze a little bit, right? Because you can imagine that, right? The idea is you have the bell curve, okay? And it's a little bit squeezed. The squeezing is depending on Z, right? If it is like more than 1, you will more spread out because more than 1 you take square is bigger, right? And if less than 1, the thing will be smaller, right? 0.5 square. So it's like you elongate more than 1, you compress less than 1, okay? And that something like this would happen. Yeah, this happened. And yeah, it compressed. So this more like compressed, more compressed to this one. Something like this would happen. I use the color. Something like this would happen, right? And this elongated, so it's like more longer. And because you double the two sides, so it's like more higher, something like that. Okay, that's how you get the thing. You get the thing. And if you add a deformed bell, many n of those, it becomes chi-square of n. So that is what it means, and that is what you need to know. It's just a definition, okay? And probably you ask why we care about this, and it will be more clear later why we need that. But for our course, we don't use chi-square directly, okay? And if you try to study the textbook, not mine, but other textbook, they would talk about categorical data analysis. Categorical data analysis. If you do medicine, medical study, this is something you would do a lot because when you look at data, it's usually not really 1, 2, 3, 4, 5, right? It's more like a medicine 1, medicine 2, medicine 3, so on and so forth. And in that case, chi-square would be very useful. Okay, but for our course, we just don't have time to look at it. But if you look at if we actually bought the textbook that we buy, then you will see there a chapter that actually uses chi-square directly. But for our purpose, we're not using it, okay? Because of I mean, as you can see, we already have very tight time schedule. We don't have time to cover those. But chi-square by itself is very useful, but we don't use it for our course directly. Indirectly, we use what we call the T and F. Actually, you will see they're built on chi-square. Okay, that's why we talk about those. So it's very simple. The following two, the T and F, are coming from the ratio. Okay, here is the ratio. T is the ratio of you have a Z. Okay, you have a standard normal Z, and the denominator is just a chi-square of M over M and take a square root. Okay, so this looks like an amazingly ugly expression, and then you ask, what is this guy? Okay, and what this guy basically is, and again, a bell curve. Actually, it's very close to the bell curve. Okay, it's very close to a standard normal. Okay, I would say this is very close to Z. Okay, very close to Z. Similar, very similar. And in fact, actually, the last line would say if M goes to infinity, actually it becomes Z. Okay, so if you add more and more chi-square at the bottom, that will become a Z. And then later you will see Y of M and more than that. But at the moment, we don't talk about those. I mean, you're clear. Actually, later you will see M is actually with the sample size. Okay, the more sample you have, then you're close to the normal. But we will talk about that this week or next week. Okay, but just look at the graph, then probably would try to make sure that you would less anxious about it, because when you see the new thing, which is you don't know what's going on, then kind of like scary. So the idea is very simple. Look at the brown one, okay, the uppermost one, okay, is standard normal, right? That is a Z, okay, and you see for the t equal to 1, okay, which is standard normal over square root of chi-square, okay, t equal to 1, okay. So basically, it's more like standard normal divided by standard normal, right? But there is still some different, right? You end up like this guy, okay, end up by a deformed shape, okay. It's like you press the head of the normal and you raise up the 2n. And here, how different from normal is like you would depress more at the top so that 2n are higher. So actually, this have a higher feather tail. So which means that the kurtosis of the T is more than 3. Okay, it has much feather tail. Okay, compared to normal. And when you increase the degree of freedom, what we call the denominator here, right? And that will lift up the peak higher, okay? Less feather tail, okay? And at the end, if you increase the degree of freedom, okay? And then at the end, you get back to normal, okay? So you to remember in your mind, T is just you should just remember as a feather normal, a feather center normal, okay? And you ask when we use it, okay? We use it when we talk about sample and the sample size is not big, okay? When sample size is big, we can use the bell curve. There's no problem with the bell curve, okay? And basically, just like you can consider a small sample size correction when you do bell curve, okay? So that basically just like when we look at the sample, we do sampling, we do calculation. When the sample size is small, we need to do some correction, and that will be the idea of T. And indeed, actually, there's not too much different when you use the bell curve, the 68, 95, 99, that empirical rule. That actually, if you use it instead of T, would not make too much difference. But here we try to make it exact, so that's why we use a student T. Okay, don't worry about it. Oh, some terminology why I have a student here. Okay, and actually why they call T as well. There's a story. Actually, later we will see why this is called T. Is in fact this is written by a mathematician and who write this research, and he sent to a journal, sent to a publisher, and under the pen name called student. Okay, so that's why it's called student T. Just he put a pen name there. Why he called student, I don't know. He should be a teacher or researcher, but anyway, he put the name called student. That is some reason why they call student. But other than that, there's no reason why. That's why they call T, because the plain name is student, and student is end with T. So I mean, no idea why it sticks to that one. But last one is called F. F is something like the following. It's a chi-square, raise of chi-square, okay? So it's chi-square of m over m and chi-square of n over n. So probably you would be wondering what it is, and the ratio. So likely is in general, it's more like bell. Okay, you look at this, it's more like bell. And in general, look like the green. The most general one is like the green one. Okay, it's a green one. It's a bell, but you can see the bell actually start from 0. Okay, actually you can say it's more like it's very similar to chi-square. Okay, but not exactly chi-square because those kind of ratio. So more you can just think about it's more like the bell curve is like this, right? But it's more looks like something like start from 0, you just squeeze things out. So more like chi-square. It's like not 0, but you just squeeze, you just push everything to here. More like I don't know what to say, but this is what it looks like. And one of the important thing here later you will see compared to T is it's not symmetric. Okay, that is one of the main key thing in your mind. The F is not symmetric. So that means that the F thing, look at the F table later, probably when we look at those, and you will see is the left and the right. You have to be careful. Okay, for the for the T and the standard normal, you don't have to worry about the left and right. The same thing, symmetric. Okay, for chi-square, actually we don't do it, but anyway, but chi-square and F, actually the two sides are different. Okay, so you have to be a little bit more careful. But I guess for F, you can imagine more like exponential, right, or like chi-square style. But that's the best I can say. Okay, any question? I mean, you will use the T and F will be using in the later stage of a course. So basically, you will not be surprised because we learned every distribution for our course already. So we just apply that for the rest of the thing. And the main thing we'll be using standard normal and the T very often. Okay, so you will be using it very soon. Okay, so don't worry, you will know how to do it by that time. But just need to know for this topic, you just need to know how to do normal. Okay. So if there's no question, any question? If no question, then let me go to the Excel. So we quickly can show you how we do calculation much faster. Okay. So I guess let's see the first function. Okay. So if a binomial, remember the big P and big F. Okay. So that is what we're trying to do. Okay. And you should notice the particular format for Excel is you would call binomial or exponential or whatever dot, and then distribution. Okay. And the key thing here is you put whatever value you want and you put the parameter here, the NP for Poisson of lambda, so on and so forth, right? And there's any three parts, right? The first part is the value you will enter. The second part is the parameters of the distribution, and the last part would be true and false. And probably you ask what's the true and false. Okay, false is always the big F. Okay, and sorry, true is the big F means. False actually means big P or small f. But discrete, then it's the big P, and for continuous, then it's small f. Okay, so actually for discrete, you only care about the big P usually, right? And sometimes you care about small f as well. But for continuous, you only mainly care about the big F, right? You never use small f, right? So let us go to Excel and actually try to do this, okay? Together, okay? And let me do it quickly. So I open Excel, okay? I'm gonna do it together with you and see how you can do the calculation. So I just follow the three input, right? So what I'm going to do is try to input this formula here, and this is actually a calculation that we use in our earlier thing. earlier class is like we calculate this guy, this example. Okay, a restaurant owner have 30% like spicy food, randomly 5 out of 2, right? So you want to see how this being calculated and how to do Excel quickly. Okay, so we have 5 customer, and how many? What's probability? So each probability of 30%. Okay, and the question is, 2 of them is good, then what's the probability, right? So asking you P of X here, okay, which is P of 2, right? How can we work this out? It just binomial distribution, okay, by NORM.DIST, and the entering the input as we have right hand X and P. X, we just put 2, and it just 5, P just 0.3, and remember when we talk about the big P is just always false. Okay, so let me do the formula test here. Okay, so hopefully you can try it on your computer and see. Okay, this is the thing we want. This is the P. Okay, and and let us also calculate this from scratch. Okay, let's calculate from scratch. This is if you remember, the formula is like this, right? 5C2.3 raised to the power 2, 0.7 raised to the power 3. This is 1 minus P, right? 3 is n minus x. Okay, if you remember this formula. So what I want to do is to show you this is the same formula here. Combination is called combine. Okay, combination 5, 2. Okay, is actually what it is here, and you times 0.3 raised to the power 2. Okay, times 0.7 raised to the power 3. So that is this solution. Okay, let me copy this here. Okay, so that is exactly how okay, this is exactly how you get the answer, right? So that's how explain Excel is very quickly. You can do this calculation, right? Of course, Excel is not for statistical calculation, so but it still is there, right? If you want, you can learn R and Python, which I think cover in the tutorial. If you have any question, you can ask the instructor in that optional tutorial. But for our purpose, that will, I mean, Excel will be sufficient. Okay, and probably I want to show you the F as well. There's a benefit of using Excel because if you calculate the big F, right, you have to calculate actually 3 items, right? Will be P of 0, P of 1, P of 2, right? So actually, big F will be calculating how many customer, what's the probability that that are less than or equal to 2 customers like the spicy food. If you remember, the question here is how many customers like spicy food, right? And if you ask the question, how many, or it's probably that 2 or less people like spicy food, then you need the big F, right? And in that case, the big F will be exactly the same formula, except you change false to true, okay? Because true will give you the big F. So that is that's a formula. Is that okay? Okay, so let me talk about the Poisson before the break, I guess, because our time is a little bit strict. So let me talk about the Poisson. So Poisson is not that difficult. Again, the same idea here. Before I go about that, you can see you can actually do the plotting, because you can just tell you what are the number, what are the supports of X, then you can basically list them out. You can plot this P. You can also plot the F. I think you know how to do the plotting. I think you can, if you want, you can just go home and reproduce this again. I don't think we need to talk about those. Okay, this is how you can draw those things by yourself, okay, if you want to know F and P, okay? Just the bar graph. Okay, I'm not going to repeat that because you should have learned that in our topic 1, right? How to draw a plot like this. So here the Poisson, you have X lambda, right, false and true. So it's just X, okay? And lambda here, okay? And let's look at the thing we do is 5, okay? So this again is out of 5, the mean of arrival is 5 people with 2, okay? So this is exactly the same question with here. Okay, it's exactly this guy, okay? This is saying you have a number of customer arriving is 5, was exactly 2, okay? So the mean is 5, right? We're asking 2, okay? So that is the question. So again, what we are doing is the probability of this would happen, right? So the idea again is just the Poisson distribution, and you put the mean is actually, I mean, the X is 2, right? The mean is 5. Again, because we're talking about the P, that is the false, okay? So we can try to do this, okay? Again, okay, we want to ask ourselves if that is a function is right, okay? And this is a very important step, okay, is whenever you're trying to use Excel, okay, actually in your work, right, and you have a new function to learn to use it, you first want to check if you're doing the right thing, okay? You have to test it, okay? So that is why what I'm doing is doing here, right? I just know what this result should be, okay? I test it with the thing I know and check whether the formula is right, right? That's very important to write programming or actually apply in practice. You have to, if you build a complicated program, to make sure that when you test it, it's already the right thing. Okay, this is a very important step. You don't just don't use it, especially sometime when you have a complicated worksheet, you add something new there. Okay, you add some new function there or add new some line there, improve. You want to make sure that once you do the change, it is consistent with something we know very well. Okay, so so that's why I just every time I do it, I show you this is correct, right? So the P of X when you do Poisson is this guy, right? E negative lambda X factorial. So this is the formula, okay? So actually we reproduce this here, okay? So E in Excel is EXP, okay? And we have negative lambda, so it's negative 5, okay? The first term is this E negative lambda. And second term in the numerator is lambda X, so it's 5 to the power 2, okay? So that is second term. The last term is denominator, which is factorial of X. So factorial in Excel is just factorial of 2, okay? So that is the, maybe I just put a bracket here to make it a little bit more easier to see, right? The exponential, negative 5 is the first term, 5 to 2 is the second term, and fact 2 is the last term, okay? So actually you can see the same formula here, right? The same number here, okay? Finally, I want to talk about the big F, okay? The big F would be the same formula except you change from the false to true. So I just copy it and I change it to true. Okay, so there's nothing deep here. But indeed, we see how quick you can do the big F, right? Because actually the F, right, this guy, right, is F of 2, right? Remember F of 2 is what? In this case, P of 0 plus P of 1 plus P of 2, right? So it's very convenient if you don't want to add up the 3 items, it's just a big F, okay? And remember what's big F of 2, right? It's asking what's probability that less than or equal to 2 customers arrive in the next hour, right? Because an hour is a Poisson following mean of 5, right? So that is making things easier, right? So And what is application, right? Just like the probability less than 2 only have a very low percentage, right? 12%, right? So if you are the you are the manager, right? You would expect more than 2 to be coming, right? So you should expect at least you have 2 clean spot for the, clean table. You have a restaurant, right? And for the purpose, okay. So let's a break of 10 minutes. So let's resume at 1:30, and then we will continue to talk about hypergeometric, exponential, and normal. Okay. So let's a break, and we'll talk in 1:30. I go around to see if any question. Okay, so we come back. So we learn binomial and Poisson. So then what left is hypergeometric. Okay, for discrete. Okay, we'll quickly go to hypergeometric. So hypergeometric again is not something complicated. Okay, it's HYPGEOM. Okay, and you notice that we have a NaN. Okay, is follow the way we define in the slide, right? So that's why you see the notation here is a very interesting, right? Just like again, just remind you what it is we have n object. Okay, out of that, A are the good object or the success object, n minus A are the bad objects. Okay, and what we are going to do is out of n we take x of them, right? Sorry, we take n of them. Sorry, we take n of them. Okay, and we're asking how x of them are the good object, right? And then that means the n minus x is the bad object, right? and we're asking what's the probability that out of the small n object, you x of them are good. Okay, so what is the probability that this thing would happen? Okay, so just to remind you. So let's again see what we have done in the what we do, right? Here is we have 30 computers in the warehouse, all of them are defective. We are going to have a sample of 6, right? So what happened is, let's write down what here is n is 30, right? Out of A, which is what we care, 4 of them defective, right? And small n is actually 6, right? X is being 2. So this is what I want to do. Okay. So let's go to hypergeometric here. Hypergeometric. Okay. So X and A N, is it right? Let me see. Is it X and A N? Yeah, X and A N. Yeah. Okay. X and A N. Okay. So X is 2, N is 6, A is 4, big N is 40, right? So we can calculate P of X. Okay. And there are 2 ways to do it, right? So let's use the formula to do it. It's called HYPGEOM.DIST, right? Sample S is 2, number of sample is 6, and population S is A, number of population is 30, and we use false. Okay. Oh, not A, so A is 4. Okay. So this is the calculation, right? And then we also know how to calculate this P of X is like, it's the following, right? Is N of N, right? Out of the big N, you draw small n of N, and out of A, you draw just X, right? And then you have N minus A, you have N minus X, right? So this is, let me draw that N. So this is the formula, right? So that means we have 3 items together. The first one is combine AX, which is out of 4 good items, you only draw 2 of them. Okay. And the next one is N minus A. N minus A is 26. Okay, that's 26 bad item. Okay, 26. You actually have to choose 2 because, sorry, choose 4 because N minus X is 4. Out of 26 bad items, you actually choose 4 of them. And the denominator is N over N, which is just 30 over 6. Okay. So you can see they have the same answer that suggests what we have done is right. Okay. So one of the interesting is to look at the F. Okay. And for those who are doing accounting, then that actually is very useful. The F is very useful in this context. Why? Remember what we are doing here is X is how many item that is less than or equal to 2, right? So it's 98%, right? Less than or equal to that. Okay. So that in some sense, if you have 2 or more, okay, or 2, or you suppose you get 3 items, okay, then it's very unlikely, right? It's only 2%. You have 2 more than 2, right? So if you get more than 2, then you would just question whether the claim that warehouse only have 4 defective will be a reasonable answer, right? That actually the way we do the inference actually what is exactly what we call hypothesis testing, which we use later. Okay, but in our class we don't use geometric distribution to do hypothesis testing, but you can see later you will see the same idea would apply in your audit case. But for our class we just focus on normal, right? And we will do normal auditing, which means that we will have a large sample, and the large sample you remember hypergeometric can be approximated by normal. Okay, but if you do a small sample, actually you do go to warehouse and do things, then in that case probably you have to be a little bit more careful about that part. Okay, so now we have all the discrete. Okay, discrete. In the case I just save in the desktop first to make sure that I don't lose it. Okay, and then let's have a continuous. Okay, for continuous, that actually we learn only 2 things. Okay, is later we'll talk about T, but we'll talk about exponential, okay, and normal. Okay, and exponential actually have 1 parameter lambda, right? If you still recall. Okay, exponential is a lambda. Okay, and you see the lambda is exactly lambda we define in our class. Okay, so lambda 1 over lambda is the mean. Okay, so here you have the false and true, and we will only use the false, only true one, because the small f we don't really use it. Okay, we use the big F. Okay, so x lambda. Okay, lambda is 2, I guess. Let me check what we have done. Oh, I see. It's the question was, okay, let's go to the question. What this guy is doing is this question of the customer that arrive follow exponential with mean 20 minutes. Okay, mean 20 minutes lambda is 1 over 20. Okay, what is the next customer arrive in the next 10 minutes? Okay, within 10 minutes. Okay, so this is 1 over 20 is 0.05. Okay, less 10 minutes. Okay, so what it's asking is the big F. Okay, big F is just exponential distribution. X is 10. Lambda is you can use 1 over 20 to make it a little bit more transparent. Okay, it's a cumulative one. Okay, so that is the answer. Okay, and we can also use the big F, okay, to calculate directly. If you remember, what's the formula? Is 1 minus e negative lambda x. Okay, so let's actually do this by scratch. It's equal to 1 minus exponential negative lambda x, so it's 0.05 times 10. Okay, or wait, that's fine. I think that's fine. Okay, so that would be the same answer here. Okay, so either you use the one we have or you do not, right? So that's the same thing. F, you just keep this too. The small f we don't really need it, so I don't demonstrate that. Okay, is that a question? The question about the exponential. Okay, if no, then let's consider the normal one. Okay, normal, actually we have 2 things. We have a standard normal, and with normal I guess I cover normal first. It doesn't really make a difference anyway. So For normal, you have to figure out that is we have mean and mu and sigma, okay? And they do not do sigma square, use sigma, so be careful what you're inputting in, okay? It's sigma square, not sigma. Sigma, not sigma square, okay? So we have the x with the mu, with the lambda, sorry, with sigma, okay? And the question I think we have is mu is this one, sigma is 4 because sigma square is 16. So I think the question is 16, I guess. Yeah, 16. So we want to know the probability that x is less than or equal to 16, right? F of x, okay? And how do you do that? It's just NORM.DIST. And we have x 16, mean 20, sigma is 4, and then use true, okay? And just to remind you, what is this guy? This guy is exactly this, with a bell curve, sorry, with a bell curve of x, okay? It's a bell thing, okay? The bell has the mean of 20 and variance, or put the SD is actually 4, okay? So which is saying the question is we're doing is 16, so it's here, okay? 16 is here. Actually, this at 1 SD, right? 1 SD here, okay? We're asking this probability here, okay? And that can directly transform to here, right? And actually, this is actually the, if you look at, if you do the calculation by yourself, actually you have to transform this to 0. This is 1, and this area is same, right? This is also the same thing. You can do this standardization, okay? Later we'll show you this is correct, okay? Z of -1, sorry. -1, okay? The same as that number. Is that clear? Okay, we will be using this very often, okay? Is there any question? Any question? Okay. So lastly, I want to show is the standard normal, okay, for our purpose, okay? Standard normal. Which is Z. It's just one number, okay? We just use -1. We just did it because that is how you transform the 20 and 4, right? And f of x, okay? F of z, okay? Here it is very similar. It's just NORM.S.DIST. And then you put -1 and always cumulative. Okay? So that's what we have. So that's explain what we have just done. You just transform it, it gives the same answer. Is that clear? That's how you get the NORM.S.DIST. Okay. And one thing I want to say here is inverse of Z. Okay. Remember one thing we said about is Z here, 0 here. Suppose we have this area. We want to find what is the number of this, right? The inverse of F, right? Inverse of F, okay? And what we do is NORM.S.inward. You just put the probability there, then we're done. So maybe I put 0.5, okay? Put 0.5, you already know what should be that number. Should be 0, right? So let's check. So that's how you get this number, okay? And also you can check, so if not 0.5, if something like, okay, 0.05, okay, then it's 1.6, okay? So if this area is 5%, okay, This is 1.64. Okay. Actually, this number you use very often. Later you will see. And the other number that you use very often is called NORM.DIST inverse 0.025. Okay. This number you also use very often. Okay. And remember, the notation we use is Z of 0.05, right? Is the other way around is 1.64, and Z of 0.025 is 1.96. Okay, these numbers are you will use very often. Okay, and the final number that you will always use it very often again is 0.05. Okay. No, I don't. You don't use. Okay, you don't use this one. You do. Oh, one. Yeah, you don't use this one. Yeah. But I think mainly use this two very often in your calculation. Okay. I guess this is pretty much of it. But don't worry, you use the calculate. You use it very often. So before we end with this Excel, I want to show you one thing. Is how we construct the Z table. Okay. As I mentioned, you can construct Z table in 10 seconds. Okay, that's how I create that for you now. Okay. So let's create Z table. Okay. And we'll construct a Z table actually based on this NORM.S.DIST. Okay. So that is not something very difficult to create. Okay. So we create a Z table. So this is F of Z, the Z table. Okay. So what we will do is we make it easier. We just construct the positive only. Okay. 0.1, 0.2. Okay. And there's a shortcut in Excel. Probably you should see this is when I try to, if you have Apple, then probably it's a little bit faster. But when you do Windows, what we'll do is if you create some sequence like this, then you just go to the right hand corner and just start dragging. The Excel will very quickly know actually what you're doing. Okay. And you can keep drag until the number you like. Okay. Okay, so that is how you get a sequence of these numbers. Okay. Is that okay? Of course, if you don't like this, there's a more smart way to do it, right? But this is what we're going to do. Okay. So let's see how you can do the Z table. Right? It's NORM.S.DIST of this guy, and then you get true. Okay. So let me put the formula test here. Okay. So here I just slow down. How I do it is you go to the right hand corner, it become a cross. Okay. And once you do this, why I put A2 because it takes this number. And this is one of the smart thing to see in Excel is go to the right hand corner, double click it when you become a black cross, then everything is there. You can do the same. So this is how you have a Z table. Okay. So you can, it's a list of the entry. Okay. And is that okay? This actually create whatever Z value you want. Okay. And probably what you want is exactly want to produce the table you see in the website, right? So how to create that is this is one dimension. This is one dimension Z table, right? This is a 1D table, right? One dimension table. Probably you want a 2-dimensional table. let me copy this and do a 2D, then do a 2D table. Okay, 2D table. How do we do it? Is here we have the first, the second decamon places. Okay, so it'll be 0 first, and then 0, 0, 1. Okay, and then you just keep drag. Okay, I think you just up to 0.9. Then actually now you have a 2-dimensional table, and then you have one more decamon point as a precision. Okay, and then the question is, how can we modify this formula A2 in a way that you can just quickly drag? Okay, so at first you will see it must be two numbers add together, must be A2 plus B1. Okay, this is the first thing we need to look at. Must be add up the row and add the column. Okay, and one thing you know is I want to copy and paste this formula, and this relative address will move along, right? But you want to keep the, say, the blue one, A2. When you move around, you need to keep the A fixed. So you put a $sign before A. Because you move, A remain the same. And then you moving this formula, you always also want to keep, for the B1, the red one, you also want to keep 1 the fixed. So you put a $sign before 1. $sign before A, $sign before 1. Okay? So when you do this, what you do is just drag and just keep dragging. Drag to I don't know how low you want to go. Okay, this it's done. So this is a table actually you've seen. Okay, and yeah, this is pretty much of it. And probably you would want to say, okay, this too many decamon places. You want to reduce the number. Maybe just only so. I only need to have a 4 decamon number. Oh, okay. So that is, once you change it, then it becomes things nicely with that one. Okay. So if you in an exam, probably you can print this out. Okay. The standard normal. Okay. So you may want to say, add this guy to decorate a little bit more. Okay. So this is the graph. This is the thing that you, if you want to use it. Okay. So really need it, then you can use it. Okay. Is that clear? Is that clear? I mean, you can do your own, but you can start from negative. If that is, you can go from negative 0.4, go all the way around. Up to you what you can want to use it. Is that okay? Is that okay how we construct a Z table? Of course, you can just print out, go to web and print out the one other people use, but you can create your own. Okay. And this table only useful only because of we don't allow you to use Excel in the exam, but actually you don't, when you know, we don't really need them. Okay. Any question? Anyone have any question? If no, then let me upload this file quickly, then we will start the sampling distribution. If there's nothing from you guys, if there's no question, I just upload it in case I forget. I just quickly upload the file. Okay. In case you want to take a look, that will be there already. Okay, it's there already. So if in case you want to take a look, then please go for it. So you can, I'll upload the assignment later today. It's right there already. So for those who arrive late, then you will see the assignment will be, the deadline will be end of, by the end of next week, is Friday. So more than 10 days to do it. And the assignment, as you will see, is very similar to the example that we cover in the class. Okay. So if you understand what's going on there, then it should not be a big thing. So a little bit more calculation, but I guess you can use Excel, will be very fast. Okay, you should be able to do within, if you know the material should be less than half an hour, right? But maybe right up you need an hour to do it, but shouldn't be a big burden to you, right? Because remember our class don't have midterm, so you should be expecting to spend some time to do exercise, right? I mean, otherwise you don't learn too much without exercise, okay? For the remaining time, I want to start the sampling distribution. And this is actually, we end the first part of our course where we focus on descriptive statistics, where we don't mention sample, okay? From now on to the rest of the whole course, we talk about sampling, okay? And they are not disconnected, and everything we learn in the first half of our course will be the basis for the second half, okay? So probability, all the thing will be subsumed in what we learn, okay? And you would ask why probability related to sampling. The main idea is being that we never, when we do studies, we are unable to have data for everything what we want to know. Okay, just like we want to know the income of the society, unless we have income of every single individual, we don't know it, right? Or we look at the health status, we're unable to do it unless we have all the data, right? So that's why when we try to draw samples, we are going to actually doing some random experiment, okay? And in that case, probability statement, probability theory will be useful, okay? So that is the reason why we learn probability so far, okay? So for sampling, actually, if you go to social science, psychology, or other subject, they actually say very big thing. How to do sample appropriately is a very complicated object, okay? But in our course, we focus on one thing we call simple random sample, which is very simple, as the name suggests, and actually it's very difficult to achieve, as I will explain later. So what is a simple random sample? The idea is very simple. It just consider the case, as I mentioned, I mean, let me define it and I explain. The first one is every element has equal probability being selected. And when you select thing, each sample is selected independent. It's very simple, right? You select thing where everything can be selected independently and then have equal chance of being selected. Okay, that means what? That means the following. Consider the case you are in a village, or you can imagine this Hong Kong, right? And there may be guy number 1 here, okay? Guy number 2 here, and guy number 3, number 4, number 5, so on and so forth, right? There are many data points, okay? And what simple random sample set is, okay? Everyone will be selected with equal chance, right? And when you select one guy, you will select the same, we will select the other guy with the same probability. Okay, very simple, right? Just like Roy die, right? And just like the probability that you will select 1 is same as probability 2, and so forth, right? This is the statement, right? Suppose the n is 1 over n, right? And the second part means this is equal probability, and you choose the second one, you choose everyone is independent, right? So the probability of 1 being selected, okay, given 2 is being selected is same as 1, okay? So it doesn't matter what you have done, okay? You have chosen, then it'll be the same, okay? So let's see why these two are difficult to achieve. Suppose you do a survey, okay? What you're going to do, the easiest thing is you go to the railway station, right? Go there and ask people come in and out, right? Because that is the place where you do the thing, right? But actually, this first violated A. Why? Because some people actually don't enter from the train station, right? Some people come from the typo road, right? From the main gate, not the straight rail. Then you miss them. A is difficult. B is also difficult. Why? Even though you, the thing is like, you're suppose you're trying to collect income data, or right, or the family background, okay, and it's likely that people actually you collected people not driving, right? Some students drive to school, right? And basically those actually they are related, right? Because it's the rich people you actually don't get. Those people you get is actually the less rich family, right? You have extremely rich people, actually they drive to the school, right? And I don't drive. I take subway, but I mean for students we are really, really rich, they will drive, right? The best cars and so on and so forth, right? So you miss those. And the other case is suppose you do a survey, right? In general case, you do a survey, right? Some very often that like you just call, right? Some people still a lot of survey just using a call. And the problem of doing a call is you basically exclude those people who don't use cell phone that much, right? And that makes things complicated, right? Or you do survey, you would exclude those people who are shy, who don't have time constraint, who don't have time to do any survey, right? Unless it's compulsory, right? So that is an issue there, okay? Or if you do a survey, you have to go to some place to do, right? Unless you do internet, right? You do internet, actually you just exclude those people who don't go do internet, right? If you go offline, then unless you go to every place in Hong Kong, you just bias, right? Because you were just excluding thing, right? If you go to Mong Kok, go to those places, then you just exclude people who don't go to that places, right? So that is not that easy to have a simple random sample, okay? But for our purpose of study, we just do simple random sample. Okay, I mean, for many of you are doing the accountancy, that's not a big deal because you go to the warehouse, you just selecting the things, okay? As long as you do the sampling, you pick up the inventory, it's random, then it's fine. But if you say, okay, this inventory looks very tall, I don't want to put it down, okay? Then in the case you're not going to select things on the top of the warehouse, okay? So that's why if you go to do it, actually you have to actually randomize, right? You actually, okay, give me the item numbers. You just toss a coin or just do some random number generator and you select, then it's fine. You will say, okay, let's pick up the first row, the first one, second row, this one, and so on and so forth. Then you don't want to pick the very tall one, then depend on your height, right? Then probably you will be some selection there. Okay. But for purpose, we just focus on simple random sample, okay? And that is when you try to learn the advanced method, okay? Later you will see you try to replicate what the property you are going to get, okay? We have simple random sample, and in the real world you can't do simple random sample, and actually the advanced method of sampling try to replicate this property. Okay, what this property here? The simple random sample, okay? The important thing is when your population with mean, mu, and sigma square, okay? Okay, so that is we don't know this two number, okay? But this is not probabilistic, this is some number we don't know. Just like the population look like this, okay? And suppose you have all the observations and you calculate the average, you calculate the variance. This is a number, a fixed number, okay? This is a number, okay? And simple random sample, what does that mean is you basically try to randomly pick up a number here, okay? Randomly pick a number here. And in that case, okay, depend on what you draw, different sample with different outcome, okay? But the good thing is it turned out to be, okay, the mean of this sample with the same mean of here. The variance of each drawn is same as this guy, okay? Because the reason is when you try to draw this, okay, the histogram, if the population, right, the idea is the following. So let's make it very clear what you're going, because it's very important, okay? So just put it this way, okay? So we have the data, remember the population here, okay? The data, this is income data. So that means that I can have an income here, or that you call X, right? And we can plot a bar graph, okay, based on this as a bar graph, a bar chart here, okay, bar graph, bar plot, okay. And this bar graph, and I can know based on the topic one, right, based on data, we can have a mean, mu, and sigma square, right? This is based on topic one we learn, right? Topic one, we have mu, summary statistic, right? We have mu, we have sigma square, right? Okay, do note that the sigma square here is based on over n, not n minus 1, because population here, right? Okay, this is the n or n minus 1, okay, not s, okay. So now the question, this is a distribution there, right? So the question is, okay, now I just randomly pick up one guy randomly, okay? And it can be any value, right? Random draw, right? Turn out to be, when you have simple random sample, because randomly pick up one guy. So this guy has a distribution, right? Because it depends on what you draw. And turn out to be the average of this number, actually, the average of this guy is just mu. Okay. And the variance of this is just sigma square. Okay. What it means is, actually, in general, in fact, it looks like this. Exactly the same thing. If you draw the P, suppose this is discrete, the P is exactly this guy, exactly what the data is. So you have a bar plot, right, from the income data, right? And when we talk about the big P, the probability, okay, it's exactly the same shape. Okay. So, I mean, probably you would little bit confused here is, suppose this is a 4, this is 5, this is 3, this is 3, right? The height, right? So why you say these are two the same? Because we talk about normalized one, right? So instead you talk about 4, this is 4, 9, 9, 12, 12, 15. So you just do this. You do a relative frequency, okay? And this graph, the bar graph, and the P will exactly the same. Is that clear what I'm saying? Okay, you have a bar plot. Instead of frequency, you have a relative frequency. Okay, just divided by total sample size. And that's with the P. And that P will be exactly the same as the random variable number you're drawing. Okay, and actually that means that the same mu and same variance. Okay, that's how we collect topic 1 and topic 3, right? Topic 1, we learn the bar graph and we learn how to calculate the mean and variance, okay? And we just learn random variable, right? We learn how to describe numbers through the big P, right? So here we just connect those, okay? So do note that now mu and sigma actually become the mean and the variance of the random variable, okay? I hope that is clear. I think that is a connection of the topic 1 and topic 3 give us what we need for this chapter. So that's why we learn things in this way. Okay. And another thing that I want to highlight is because independent, which means that different observations have zero covariance. Okay. Here, although I just mentioned about the mean and variance, indeed, if you learn further, for those who care, actually is the skewness, all right, will be same as the population one. And if your kurtosis, that will be same as the population one, right? The population, you can calculate skewness, you can typical kurtosis, right? Because, and then if we don't define this, right? But it will be the same, right? Because the idea is they have the same shape, everything the same, okay? But do note they're different, right? One is when you talk about expectation, when you talk about the description of the random variable, okay? It's before you draw it, that is what it looks like, okay? And this is data, okay? Is that clear? You have to know the distinction of the two. Okay. Finally, I want to mention one key point here, but we don't have time to do that. That is very important. It's called sample mean. Okay. This we'll talk about more in the next class. Is because each observation here, average of this observation is called sample mean, and this guy is a random variable. The reason is because it depends on the sample. Okay, the sample mean is the mean of the observation of a sample, which is random variable. It's very important. We'll talk about this next class. Okay, so I think the time is up. So we'll talk about the next class. I see you on Wednesday.